Uh, yes. So the next session is on why think by Nicholas. So Nicholas, over to you.
Yep. Okay, sound check before I begin, since that's been a problem before. Can you all hear me?
Yes.
Okay,
Yes.
great. So this is basically looking into a question that's related to what Thomas commented on in his talk, that in an information theory sense, the information in the universe never increases. And we have this sort of thought that, like, if we made an AI that was somehow human-like, it could engage in human-like activities that do seem like, if you just sit and think in a vacuum, you would benefit. So why do mathematicians sit and think when they can't possibly be generating more information about the world? So that's going to be the main theme of this talk. And I will say up front, this is going to show a lot of results that are in the sense of like developing machine learning models failures, that they perform significantly under state of the art. And it's more to see whether or not there are sort of consequences of certain design decisions. But some of these things actually do kind of work. And maybe there's a way of salvaging them or turning them into something worth using for something real. But that's the caveat before I get too much into it. So yeah, don't be surprised if you see things that are like 100 times worse than state of the art. Okay. So a lot of what we do in machine learning nowadays, there's a tendency to frame this as inference, no matter what we're, even though we're just training against some loss function, these loss functions can be interpreted with respect to things like information theoretic quantities. So if we're doing, P of y given x with cross entropy, well, training against the cross entropy or the KL divergence induces the output of the model to behave like something that should be a P of y given x rather than just some arbitrary output. And similarly, if we're doing regression with, say, mean squared error, there is a way to frame that as, okay, I have the family of Gaussians and I'm finding Gaussians with unit standard deviation, and I'm doing inference on the parameter of that family of distributions. In reinforcement learning, you might be just outputting a policy, but you could reframe that as saying you're predicting the probability that a given action will be the best action you could take in that circumstance, or the action that the thing you're imitating would take, or something like that. And all of these kinds of inference problems fit very nicely into information theory. So a lot of the time you can say, well, how well a model does is the amount, basically it's how much mutual information does it actually capture between the input variables and the thing it's trying to predict, where that mutual information would be the best it could possibly do, because that's the amount of information that it gets to know about the target, given a perfect inference engine on its input. And of course, it'll do worse than that in practice. But you are trying to kind of like push the model to that asymptotic limit. And this kind of leads to ways of talking about what neural networks do as sort of being an information bottleneck. So you can't ever produce information, it's already there, but all you can do is kind of purify it. And you do that by discarding the stuff that doesn't actually predict your target, or that is sort of irrelevant to your target. So every time you pass something through a layer of a neural network, you're just throwing out information. It's a filter. It's not any kind of like algorithm or active generator. It's just a very complicated nonlinear filter that is acting on informational spaces rather than on directly on like the linear representations. Um, so once you've removed information, you can't get it back. And every time I apply one of these layers, ideally, I'll only be removing things that don't tell me about my target. But like in practice, I'm going to remove a little bit of stuff that does tell me about the target anyway, because my layers are all approximations. They're not going to be perfect. So in some sense, like once I've already gotten to a certain level of quality, I can only get worse by adding more layers, or I can only get worse by thinking longer. And you also have this kind of issue that there's really no difference from the information theory point of view between doing this like one step at a time and doing it all at once, because information theory doesn't care about representations. So, I might as well just say, okay, these are arbitrary functions, and I could just discard all the information that is not relevant to my target in one step, rather than breaking it down layer by layer by layer. And if we think about something like the act of thinking in, say, a recurrent network or some kind of recurrent agent as being, reiterating the same sorts of processes or dynamical system rules on its hidden state, then this doesn't really put us in a good position for understanding why that might be beneficial or how to take advantage of that. So there's this kind of contrast between the world as seen by the information theory account of a neural network and the sort of human experience that, well, sometimes if I sit and think, it feels like I'm making information from nothing. It feels like I'm noticing something about the world that I didn't see before somehow. So, after that, I can say colloquially, I have more information about this thing I've been thinking about than before I thought. But of course, like from a strict information theory point of view, that wouldn't be true. When a mathematician goes and derives things from axioms, the axioms the axiom already contained all of the stuff that the mathematician derived in a way, and they're not like producing something from nothing, but in practice, you still have to go and do that. There's also the observation that there are algorithms, so I don't have to just use human experience as a touchstone, since that can be a bit unreliable. But there are algorithms where you do get scaling benefits from adding additional computation time, like a Monte Carlo tree search. If I add more compute without changing the inputs to the algorithm, uh, I'll get closer and closer and closer to higher quality solutions. And there is some sort of like, this isn't just convergence of the last percent of accuracy, but the solutions often feel qualitatively different if I run like a Go engine for a short time or a long time. So we want to have some way of actually explaining what's going on here so that we can build in these elements and we can make architectures that can take advantage of this kind of scaling compute. Or in the case of something like Badger, we have this idea that we'll have a scaling number of experts. And how do you get a benefit from increasing the number of experts? It has the same kind of paradox. It can't be that the benefit is that they produce information. It has to be that somehow by providing that extra compute, they do something you couldn't do with less compute. So, in Badger, we have a lot of choices to make because it has this kind of nested structure. I don't, for what it's worth, I don't think you have to take like the entire contents of this talk as being about Badger, but this is sort of maybe this is the motivation of why we're doing this at Good AI. That you have an outer loop where you figure out this expert policy, but even the inner loop has a lot of substructure because you might expect, you want this thing to do online learning, so you're going to see multiple tasks within a lifetime. A task doesn't mean like a single in out, but it's actually a period of time interacting with the environment. And even within a single interaction, the agents, like the experts inside Badger, are going to be talking to each other because you have this graph neural network understructure and you have to have message passing on the graph. And like we heard in Deepak's talk, it actually matters that information gets across the graph. So maybe you only need to do one upward step and one downward step if you have a tree structure, or a couple steps if you have a loop. But there's also this thought, like, would it be good if I made this communication period of time like really long? What if I gave it 100,000 steps before taking the next action? Would that be better? I mean, empirically, what we've seen is for the architectures we've tried, the answer is no. But if there would be some way to change the architecture so that it could actually get a benefit, that would be interesting. And there's also this thing where we have this possibility of needing a warm-up phase, because the Badger experts, either they have to figure out how they're connected or they have to decide how to connect to each other. And that means in some sense working out like, basically breaking a lot of symmetries by iteratively sort of negotiating, who's going to pay attention to whom, where are the links, things like that. And so should we have a few warm-up steps? Should we have a lot of warm-up steps? Should we have no warm-up steps at all? What's the benefit of doing this kind of warm-up? Does it even make sense? And in the information theoretic point of view of neural networks, all of these things should be as short as possible. So this is kind of saying, is that really true, or does that need to be true? Also, of course, there's the number of experts. If it's not coupled to environmental issues, like if you don't have some kind of modularity in the environment, is there ever a benefit for having, say, 100 times as many experts as you really need? And how would you derive benefit from that? Okay, so I'm going to propose that there's kind of two routes of thinking about what's going on with this kind of, shall we say, this illusion that the information is increasing. One of these routes says it is an illusion, but it's one that matters. The other route says, no, actually the information is increasing. And then there's actually quite a lot of connection between these two routes, where they're not it's not 100% clear that everything in the information increasing route isn't about the what is going to be the computational access route. So the first route is this idea that I might have information in a variable, but that doesn't mean that the computational device that is performing the inference is able to use that information. So there was a recent paper, a theory of usable information and computational constraints, and they basically formalize this concept of a usable information, which is always less than the mutual information, and that is defined under a certain model family or model class. So you might have the class of linear models or the class of polynomial models or three-layer neural networks or something like that. And given that class, you can estimate how much of the mutual information between X and Y that can extract. So in this picture, the more computation I do, if the computation is kind of purposeful or useful, I'm increasing the usable information while I'm decreasing the irrelevant information. And so there's this kind of optimum point where if I don't do enough computation, I might have a smaller chance that I've discarded something relevant about Y, but I also haven't unearthed all of the information that is relevant about Y in a form that the terminal layer can access, which might be a linear layer. If I do too much, then I've already had enough time to disentangle everything so my final layer can deal with it. But now I'm just starting to discard stuff that I don't want to actually discard. And then the other path is the idea that in a lot of the problems where it seems like sitting and thinking is useful, you actually kind of have all of the information to define the problem family already. And what you're doing is you're kind of querying an internal model of that problem. So you're querying this kind of oracle that tells you something you don't have explicit access to. So if I'm solving traveling salesman, I've got an oracle that says how good my solution is. But in practice, I have to search that infinite or exponentially combinatorically large solution space. And the thing that my search algorithm gets isn't the knowledge of the entire structure of the space, but it's a set of attempts and what their value was. So every time I sample from this model, I'm in some sense transferring information from the model into my inference process. And even if the model can be summarized in a very, very condensed way, like traveling salesman problem can be defined in a sentence, the way that I'm transferring information into my inference engine, it can't work with that representation. So this is the commonality with the usability picture. But in the end, I can actually generate entropy because I'm doing the sampling process. So every question I choose, if I'm sampling that question out of a distribution, I'm actually creating new entropy because there's this new random process in the system that wasn't there before. And in this picture, the information that I have isn't about the external world. It's actually about internal virtual variables. And I can always make that information unboundedly large just by generating more internal variables that I want to have relations between. So, instead of traveling salesman, you could think maybe the model is something like a cellular automaton, and I want to find all of the gliders in the cellular automaton or something like that. Having the rules is not the same as having a list of all the gliders, and I can kind of decompress those rules into arbitrarily large quantities of bits in a way that would be useful for doing something or other. So this kind of point of view means that when we, from this perspective, when we sit and think, we actually are generating information, but it's information about, in some sense, something that's already contained in ourselves, rather than information about the world. Okay, so this is now going to be about 10 slides about the usable information, then the rest will be about the information generation perspective. So I'm taking a bit of a shortcut compared to the paper. They actually they define something that they call the predictive entropy, which they use in place of the Shannon entropy, and it's also under a model family, but basically it's almost always going to be equal to the Shannon entropy. So I'm just going to cut that short and go straight to the Shannon entropy. And essentially what the usable information is it's the portion of this entropy that can be reconstructed by the best predictor that is drawn from a model family of a certain type F here, which, as I said, it could be linear models, neural networks, etc. It has some nice properties. It's always going to be less than or equal to the mutual information. And the other kind of thing about it that's interesting is that it's not the same from X to Y as Y to X. So representation does matter. And if the model family, has asymmetries that can it can push those asymmetries into the usable information. This basically is directly going to tell you how good your neural network can possibly be if you're training it to do a prediction task. So it's also a bit more directly relevant than the mutual information, or it's when you actually evaluate your loss function. This is closer to what you're actually evaluating than the true mutual information. There are various bottlenecks that can limit it. So a lot of the experiments that follow are going to be trying to pull apart these bottlenecks and understand where each of these things are applying, because they kind of suggests things about architecture design, what you should focus on. So one perspective is that actually you just need, you might have some very nonlinear function, and that nonlinear function just cannot be computed without a certain number of cycles. Like it just is that hard to actually form that map. Another is that you could have an information flow issue where, let's say I'm talking about a convnet. The convnet filters have a receptive field, and if I need to integrate information from two sides of the image and my receptive field is smaller than the size of the image, there are going to be certain things I can't infer. If, for instance, the pixels on the left and the pixels on the right contain information which is synergetic with respect to the prediction target. And synergy here means that the mutual information between the target and both of the observations together is higher than the sum of the mutual informations between the observations and the target apart, right? So that kind of thing can happen. A classic example of that is XOR. If I have A XOR B and I want the mutual information between, let's say I define Y is equal to A XOR B, I want the mutual information between A and Y or B and Y, then it's basically I can't predict Y. But if I have A and B together, I can predict Y. So if I have these internal structures in my model that have some kind of limitation of the receptive field or the way in which parts of the representation can be combined together, then by doing more computation, I can expand that receptive field. I can allow the pathways for information to flow through. This is the kind of relevant perspective for the message passing on graphs. If the radius of my graph in something like Deepak's work is 10, and I do fewer than 10 message passing steps, then I'm not going to get a signal from one side to the other, unless I do something where like I exploit the tree structure and I do those steps sequentially rather than in parallel. The thing that is, I think, quite common now with over-parameterized deep learning models is actually it seems like capacity does a lot more than computation in a lot of these cases. So I may just need to memorize a lot of parameters or a lot of things about my data set in order to formulate the map in a way that properly infers Y from X. This is not necessarily the same as computation, but they can kind of trade off from each other. So an example would be if I knew the function family that I was in, then maybe I could represent the actual map from Y to X with only a handful of bits. But if I'm trying to approximate that function family with like a Fourier basis or Taylor expansion, I may need many, many more bits to do it. And it's just that I have to store like every single, okay, like a sinusoid, for example, I need an infinite number of bits to specify a sinusoid from a piecewise linear description. But if I just say my family is sinusoids, then I just need the two floating point numbers of the phase, well, the amplitude, the phase, and the frequency, so 3. And then finally, and this is something that they don't really get into in the usable information paper so much, there's trainability. Because in practice, I don't just get to find the best F, like I don't get to find the best model in my function family. I have to actually search for it using some kind of procedure, usually some SGD or evolution or some search procedure. So there may be things that would be better, but I'm just never going to be able to find them. And this is just a very simple toy example to sort of show how you can look at the scalings and kind of interpret those scalings in terms of these different things. So the task here is I have this kind of sine wave, or sorry, not sine wave. I have the square wave that varies with respect to the input, which is a one-dimensional input x here, and then my class is either 1 or 0, alternating at some frequency. The blue is the target, and then the orange is a bunch of different RNNs or DNNs that are trying to predict the target. And what
Nicholas, we lost you. We can't hear you now.
did I lose? Am I still here?
Now we can hear you.
Okay, yeah, anyway. So what is the recurrence in this RNN? So the recurrence here is not like reading the X values in sequence. It's actually taking one X value and repeatedly operating on that X value with the fixed weight matrix. Okay, so here I have a single layer definition, and it has a one-dimensional input plus its hidden state of dimension n. And I apply the layer, I get a new hidden state of dimension n. I put in the same X again, and I iterate for a number of layers equal to depth, and then softmax and cross entropy to train. Versus a dense neural network where the only difference between these two is that now I can have different parameters on each layer. Okay, so like the computational power is based on the depth, but the capacity will be higher in the case of the DNN than it would be for the RNN because I have more parameters. And so what we see is that in general, the depth does matter both for the DNN and the RNN, but capacity actually in this task, even though this task is it's a square wave and it has only a phase and a frequency. If I'm going to fit a neural network to this function, I actually need capacity because for the same depth, the DNN, especially for intermediate values of the width of the layers, the DNN actually increases its usable information between X and Y more quickly. So this gap here between the dashed line and the solid line is sort of the capacity effect. The general scaling as I increase the depth is for the RNN is the computational effect. There is no information bottleneck effect here because it's dense, so it's all to all. And the other thing to notice is that the error bars on these things, this is the standard deviation of the distribution of usable information that I estimate run to run. So formally, the usable information should be the maximum of this envelope of curves for each of these cases, right? It's the best possible model from the model family F. But in practice, I may have a lot of models that never get even close. So for this kind of problem, especially as I go to increasing depth, the trainability ends up being the main bottleneck. And just another way to visualize the same data, here I plotted parameter count versus the usable information, and the different curves are now different depths rather than different widths. And so you can kind of see that like increasing the parameter count, there's generally a positive effect here. But as the as the depths get bigger, there is maybe some kind of place where basically if you have a deep enough RNN, you don't need more parameters than that amount, right? So like this, the green curve and the red curve have different depths, but they're basically almost on top of each other. And around this 200 parameter count, they're coming quite close to saturation. So I would expect if we went to depth 16, depth 32, et cetera, if the trainability wasn't a problem, because in practice, when you actually go to those depths, these curves start to dip back down because they become untrainable for the set of parameters I use to train these things. But if you resolve the trainability, you'd basically see that this thing comes into the black line quite sharply. Okay, so that's sort of an example of what you can get by looking at the usable information and how you can kind of see these different kinds of bottlenecks in the way that things scale. Okay, so that's all well and good. It seems like, in fact, computation can get you something. That's great. Now let's try to bite off more than we can chew, and let's see if this violates no free lunch. Can we actually come up with some kind of universal quantity that doesn't depend on the task, such that this representation is just better than that representation given a model family? right? So the hope of doing this is that, well, if I don't know anything, I can't do better than random, but I know the model family. And if I know that I'm working with linear models or something like that, that information should let me do better than just random representations. So we want to define this quantity that basically tells us what we would expect the usable information to be starting from the representation X for some unknown task Y. And it's a little ill-defined. We have to do some work to define it. So we're going to try a couple of different things. We could say, let's find the easiest problem, and the accessible entropy is the usable information from X to the easiest possible problem that I could define mapping X to something. This is nice because the usable information is always going to be less than this quantity, and also this quantity is less than the Shannon entropy. That's good. We could do the hardest problem Y. That would be really useful if we could maximize that, because we know that the usable information will always be greater than that lower bound of the accessible entropy. So if we had a high lower bound, then this representation, it would be possible to solve any problem to at least that quality, that where the Shannon entropy permits it. So that's good. The problem is, in practice, this thing is usually going to be 0, because I can define y of x equals 0 times x or something like that. I can basically just zero out the entropy of y, or make y just a random. Sorry, I should make y just random, and then basically it's impossible to infer it, so my lower bound will be 0. So in practice, what we kind of work with is this contrastive accessible entropy, where we find a problem that maximizes the contrast between the best model in F and sort of the best possible model. The downside of this is we've lost any kind of strong relationship between a given usable information and this entropy. But the upside is at least this thing should usually be non-zero, and it's also like a reasonably hard bound, because we try to find the hardest problem that's still solvable somehow. So, all right, basic sanity check. Is this even possible? There is an example from classic machine learning that shows that, yes, in fact, this is possible and actually quite easy. If I take a low-dimensional representation of something and then I just map it to a high-dimensional space through random embeddings, often that improves the performance of most models from most families of model, especially if I have things like linear models that literally cannot represent the data. So here on the top, I have XOR, blue, blue, red, red. If you can't see it, I know the palette's a bit tricky. And if I fit a linear model, of course, nothing happens, because you can't separate these with a plane, with a decision boundary. If I map up with a random forest embedding, then even the linear model can basically do XOR. Similarly, I can shatter a set of random points by doing a embedding in high dimension and then fitting a linear model, when I can't shatter those points with the linear model. I know shattering points is usually not something you want to do, but this is about capacity to express certain functions more than generalization at this point. So yes, in this sense, we should expect that it is possible for some representations to just be better. So, okay, so we have that, we have some definitions. Now let's try to actually train something to make it big and see if that helps us. And what we're going to do is use adversarial training to find that task set, and then evaluate S, and then try to make a transform that makes S bigger for a given input variable. I'm going to go over this quickly because it basically is terrible. So the random embedding, this is CIFAR images, and what I'm going to do is I'm going to train this preprocessor on the accessible entropy without knowing what the labels of the images are. So I'm going to invent tasks on CIFAR images to try to make this representation better. And I can get when I then take those representations and train CIFAR on them, and I'm fixing these representations to have the same number of dimensions as the input, then I can get like a 2.4% improvement on what a linear model can do with CIFAR. And I should say, these losses are terrible. So I was warning you, this is not going to be anywhere near state of the art. The reason is because I'm literally using a linear model for the final layer. And linear models on CIFAR with a receptive field of 5 pixels are not going to do very well no matter what. But if I do a random embedding up to 100 dimensions, then I can get a 13% improvement, no problem. So it kind of works, but you probably would never want to actually do this. There are better things to do. if you just want to classify so far. But it's interesting to know that there is some kind of sense in which some representations are intrinsically better, and you could, in principle, imagine an AI that is somehow making use of thinking time by re-representing data it already has in a way that's more accessible to its downstream elements. Okay, so conclusions of this, it really does seem like computation is useful, but capacity in the kinds of problems we tend to think of is more important than computation. And trainability is very important. And a lot of the things we would do to increase computation also have a cost to trainability. So we're kind of sitting in this place where we might be gaining a lot of bad trade-offs by trying to increase the computational power of our models. So this route is kind of not super promising for finding a way of like taking advantage of 100 million Badger experts or something like that. And in terms of this accessible entropy idea, well, there are a couple of things that we could have concluded, like that this usable information really depends more on knowing the relationship between X and Y than the structure of X. But up projection kind of falsifies that idea, since up projection doesn't know about Y. And it may also be that this idea of using anchor tasks to define this thing is just not a very good idea. So that there might be some better definition, which may or may not be computable. Of course, that's always the trade-off, that would actually find representations that do work better. And there have been a lot of successes in unsupervised representation learning. So this is probably not impossible, but this particular route to it may not be the best. Okay, that's route one. I'm going very fast because I don't have that much time, but like, please stop me if you're lost. No? Okay. So route two. Here, this is going to focus on the idea of using sampling and search. This stuff, I call it program synthesis, but it's different than the traditional program synthesis. This is really quite similar to the modular meta learning stuff we heard about yesterday and the routing network stuff. And the idea here is going to be that I'm going to be doing some kind of search at inference time over a set of compositions of modules to make a sort of program to solve a task, but that will be that will make use of this oracle that I get that will tell me sort of how good my solution is or how good my intermediate solution is. And I'm transferring information from the oracle into the program. From the big picture, the idea here may be that like when I train these things, I am also generating some kind of information in the module weights, because we also, the modules here are neural networks like in the modular meta learning papers. And so we are actually learning something, but the thing that we're learning about isn't necessarily going to be about the tasks. It's actually going to be about the agent in some sense. So about the computational structure of the modules, about the nature of the search process, the composability. And if that's the case, since this is a hypothesis, we don't get to say that it will be the case. If it's the case, then we should see some kind of task independent benefits from these trained modules, which would normally be framed as meta learning. But also that by sharing this between agents, we might see benefits as well. So that even if I have two agents that are trained on completely disjoint sets of tasks, transferring a module from from an agent trained on one task distribution to another task distribution may actually still be beneficial. That's the kind of thing we're going to look for. The reason why we're interested in that last point is, again, thinking about Badger being a internally multi-agent system. If you have this internal like replication, and if you want to distribute this, have everyone who is using the architecture, share the modules that their problem induces into some central repository and distribute them back among all the other users, you'd hope you'd get some kind of synergistic benefit, or maybe you could engineer it to get some synergistic benefit if this is true. Okay, so it's, as I said, it's inspired by program synthesis, but we're going to have learnable primitives. We have a repertoire of these operators, and then the operators are chained together into programs. I'm going to talk about two different ways that we did this, one through combinatorial search, where the programs are literally linear sequences, and the other is closer to the routing networks, where we are going to have a weighted combination of operators at every step of the program. And then we will learn those weightings via gradient descent at inference time. So that's the main difference between this and the routing networks. We don't have a network that predicts the program, but rather we're actually going to allow some backpropagation into the program structure itself to learn the weights. And what it turns out, just to get to the punchline, is the combinatorial search doesn't work very well, except on like one problem where it works shockingly well. And then the gradient descent generally works pretty well. But it still doesn't work as well as like a traditional machine learning method on, simple problems. Okay, so the way that the first set is the combinatorial search experiments. Here we're doing a toy data set of 8-dimensional Gaussians. These are PCA projections, and you can see they're quite separable. If I train support vector classifier on these things, the loss is like 0.06. The accuracy is basically 100%, almost 99 point something. And the way that these programs are going to work is that the programs are neural networks that apply to a bank of registers, and they have a scratch space and also a place where the data is, the 8 dimensions of the Gaussians are injected. Every class has its own program that's being induced, and the outputs of the program, the final outputs of the programs, are passed through a linear layer and softmaxed to get predictions. In order to search these programs, we're doing a combinatorial search using something called fractal. This is basically a variant of Monte Carlo tree search, but it generates the programs in a sort of step forward way, and it has a novelty search term that encourages keeping around programs that might have lower reward but have a higher diversity. Okay, so the repertoire is in this case going to be 15 operators. And once we find the programs for one instance of this task, what we're going to do is we're going to back propagate into the operators to update the operator weights. And then what we could do is we could have multiple repertoires and exchange modules that are used very frequently by some repertoires for modules that are used infrequently in others. So we basically could say, all right, maybe I have a dead module, like what was described in yesterday's talk by Clemens. In that case, the dead module would not be used very often, and so it would be randomly replaced by something from one of the other repertoires. And we can do this because we're constantly rediscovering the programs, so we don't have this inertia of like module 3 is module 3, and I know how to use module 3 as the function it represents. It can change, and it should still work. And what we see is that, well, first of all, just the sort of disclaimer: chance level here is 1.8. Classic machine learning is 0.06. These numbers are in the 0.55 to 0.95 range, so this is absolutely terrible. But we do see, especially if the search is weak, that module exchange is beneficial. So what this is kind of suggesting is that this idea of the intrinsic information about the search is probably not really true when the search is strong. We're not getting any synergistic benefits when we have 128 walkers is like the number of Monte Carlo tree search steps times it would be times 10 or 20 or something like that. But when the search is weak, somehow there is this kind of information about which modules are findable or which modules are searchable. And by exchanging the modules between agents, they're able to sort of solve that problem about their own cognitive architecture a little bit better, but still much worse than classic machine learning. For what it's worth, if you do this with the gradient-based programs, it still doesn't do very well. It gets around 0.4. So there is something about the formulation about this architecture that's probably inappropriate for this kind of classification problem. But, caveats. All right, something that actually does work is image generation. So here, we're going to generate CIFAR images from a 0 image. And the idea is to find a program for each training set image that reconstructs that image starting from 0. So this is like encoding images into programs. It's not an autoencoder, right? The image is never input into a neural network. The place where the image comes in is through the oracle. And the oracle then discovers the program that reconstructs that image. The operators are 4-layer convnets. It's good for these operators to be diverse. So we have a couple of things that we allow to vary, like they can have a skip connection or not. They can have either ELU or sign activation function. We also use a Fourier feature network kind of input positional encoding, since that makes this sort of image reconstruction generally better all around. And there's going to be two, as before, there are two kinds of backprop. There's backprop at inference time into the program, and backprop at training time into the modules. And because we are learning the program incrementally, we do try to keep the program around over multiple outer loop steps. So we don't delete and restart the program every time. That it makes a huge improvement in what we see if we can keep around the old programs, although that does mean that we're a little bit more brittle if we change the operators too much. This is what running the program looks like. And basically, you can see that the changes to the image are gradual, but you don't actually see what the final image is like until almost at the very end of the program. And this is kind of an important difference between this approach. Sorry about that, my headset keeps turning off. A difference between this approach and the previous one here. With this fractal search, I kind of have to be like getting closer and closer and closer to a good answer as I extend the program length. But with gradient descent, I don't have to get closer to the answer before the very end. So that I think that helps quite a lot in finding these programs, in increasing the expressive power of these programs. This is what we see with outer loop and inner loop epoch. So the inner loop is the number of steps of gradient descent on the program. The outer loop is the number of gradient descent steps on the modules. And it's trained on 500 images out of CIFAR. It's tested on a disjoint set. It's also tested on MNIST images. And that's, I think, the first cool result in this talk. So I probably should have led with it, that this actually can reconstruct MNIST images about as well as it can reconstruct CIFAR images. So this actually generalizes out of data set quite readily. It also seems like this is, unlike the other one, which was sort of saturating at a very bad result, this seems to be converging. If you train it longer, it gets better. It doesn't get better, in a particularly happy way, since it's some 1/√x type curve, which will take forever to get too much better. And you'd hope to see exponential convergence, but I'll take it. You can kind of see that the longer the outer loop goes, the deeper into the inner loop I can see benefits. So early on, I do saturate with the inner loop. Running the sort of inference time optimization is not helping me, but the longer the outer loop runs, in some sense, the deeper this inner loop can converge. And so that relationship is sort of a bound that we have to be aware of, because what we would have hoped is that I could think for an arbitrary amount of time, like just to remind the point of this inner loop thing is the thinking time in the why think, right? So I would have hoped that I could have thought forever and got open-ended benefits, but it does depend on how deeply I'm trained in the outer loop. So some kinds of modules are more searchable than others, or are more composable than others. And this training process discovers them. Yeah.
How many inner loop steps you are doing during training?
So as I said, I keep the programs around. So by the time I get to 10⁻³ in the outer loop, the programs of the training set have seen 10⁻³ inner loop steps as well.
Okay, thanks.
Mm-hmm.
If I can add, I mean, that might explain also this bound a bit, right?
Yeah, it definitely, if I reset the inner loop, if I reset the programs, then it doesn't converge quite as well. So that is ongoing. That is an ongoing issue. Okay. Here's the pretty picture. So you can see on the right, you have the reference images, and on the left, you have the reconstructions. The top 4 are training set, the middle are test set, and the bottom are MNIST. The transfer to MNIST is quite good. For reference, when I train an autoencoder on the same thing, and to get the same 0.018 loss that I see on MNIST, I need about 15,000 CIFAR images to get there. So at least we see this data efficiency that we would hope. That's maybe the one thing that I can say is better than traditional machine learning about this approach so far. That at least in that sense, this kind of synthesis allows us to express things that are very far outside of the training set. And that expressiveness, I think, is kind of the path, or one of the things that we want out of combinatorial generalization. So that would be the one reason why I would say, like, give this the time of day, is because that property of being able to express things outside of the training set, not maybe generalize to or be able to perform well, but just to express it is going to be necessary if we want to have some kind of generality in AI that extends to problems that are more complicated than the problems that the AI has been trained on. Right. That's the sort of thing with language. I can learn language to say like go, north, east, west, south, and I can give you directions to go from my house to my office or something like that. Okay, how about the exchange mechanism? With gradient descent, this isn't very happy. Part of the reason is because the inertia in the programs seems to matter, but I corrected for that by basically having like this adaptation period and then only keeping the exchange if it made the result better. And what we find is that there's no effect. So module exchange with gradient descent, you might as well not bother. One agent is as good as 8 agents. One repertoire is as good as 8. There might be some effect at short time, but it's honestly, it's so small, like you would never do it intentionally. So this idea that we're learning, significant intrinsic information about the agents doesn't seem to be panning out. Okay, so what do we have? Well, there should be an extra slide, but so we can learn transfer between tasks, right? Like I transferred from CIFAR to MNIST, so that at least seems to be general. But at the same time, we can't transfer this between agents in a way that's more useful than just learning it on your own. And so there is kind of a question of why is it that we are seeing this between task transfer, which is so good, but at the same time, the transfer between agents is basically worthless. Is it because gradient descent is just such a powerful method that you don't actually need to have much intrinsic information about the modules to make them discoverable? That doesn't seem to necessarily be the case because of that effect where the inner loop trainability extends when you go deeper into the outer loop. So I don't yet understand why this exchange is not getting us anything. And yeah, I think probably at this point I should stop and we should go over to questions.